The atmospheric pressure chemical ionization (APCI) source works in a manner very similar to ESI, except that there is no voltage at the tip of the capillary tube. The solution containing the sample is sprayed out of the capillary tube at high temperature to aid the desolvation, and then it is subjected to a high voltage delivered by a needle called the corona needle or corona pin. The charged ions now present in gas phase are pulled into the sample cone by the same vacuum as in ESI. The electric discharge from the corona pin causes the ionization, but we should note that this is a much higher charge than delivered at the tip of the capillary tube in ESI, which limits its use to thermally stable molecules. In addition, both ESI and APCI work well for small molecules. Small molecules are those that weigh less than 1500 daltons. MALDI, or matrix-assisted laser desorption ionization, is a completely different mode of ionization. First and foremost, the sample has to be deposited on a solid surface in a mixture with small molecules that can absorb a lot of energy, what is called the matrix. The mixture is allowed to dry and is then hit with a UV laser beam that causes the matrix to absorb energy and eventually explode off the metal holder. This vaporization in a high-energy environment also favors the exchange of a proton between the matrix and the analytes, which causes them to become ions with a charge of +1. MALDI is most commonly seen in food sector in tandem with time-of-flight mass spectrometry, TOF, or for imaging purposes. In imaging, a spatially organized system is raster scanned with the laser, and the chemical composition is elucidated for each position. This is typically not used in food safety. Here's a promotional video from Brooker that explains MALDI TOF.
The MALDI TOF process is a two-phase procedure. Initially, the samples are fixed in a crystalline matrix. In the initial ionization step, they're bombarded by a laser. The sample molecules vaporize into the vacuum while being ionized at the same time. High voltage is then applied to accelerate the charged particles. The second step is the time-of-flight mass spectrometry phase. In the linear mode, particles will impinge upon the linear detector within a few nanoseconds after ionization. Higher mass molecules will arrive later than lighter ones. Flight time measurements make it possible to determine molecular masses directly. Each peak in the spectrum corresponds to the specific mass of the particle along the time axis, starting with the ionization moment. In the reflector mode, the particles are diverted so that they fly towards a second detector. In addition to extending the flight distance, the reflector also focuses the masses. The combination of these two effects makes for higher resolution than in the linear node.
Electron ionization, EI, happens when a sample stream is bombarded with electrons. This can produce both dissociative and non-dissociative ions. EI is the most common source of ionization in GCMS for food safety. MS is quite simply the combination of two quadrupoles in series. The first quadrupole receives the sample from the source, usually cleaned up or concentrated using a proprietary design, and selectively allows the ions meeting the target mass-to-charge ratio through and to the collision chamber. These ions are known as the precursor ions. They used to be called parent ion, but the term has been replaced with precursor. The collision chamber, which is called the second quadrupole by some vendors, is a cell filled with argon gas where the ions that made it through the first quadrupole are subjected to a high level of collision energy. The parent ion breaks and forms a number of different product ions, previously known as daughter ions. These products can be close in mass-to-charge ratio if the portion that was knocked off is small, or they can be very small. Ideally, we select larger product ions for conformation purposes, as smaller ions can be produced by breaking too many different types of parent ions. They consequently lack specificity. In summary, the ideal precursor ion is the molecular ion in LCMS produced by the source, and it therefore has the molecular weight of the compound of interest plus or minus 1, and then divided by a charge of 1. And the ideal product ions are those that keep most of the chemical structure of the parent and are thereby not easily formed by many different parent ions. When using single MS, we ideally want to obtain the molecular ion as the first criteria for identification, and then adducts that maintain as much of the chemical structure of the parent ion as these are more specific. In all cases, it's important to be able to justify the formation of the adducts from the parent chemically to avoid analyzing ions that may originate from contaminants or compounds originating from the sample matrix that were not removed during sample preparation. When only one MS is used and the ion goes to the detector, the instrument is known as just MS. But this is not the only option. The ion can be directed to a time-of-flight chamber, in which case it becomes MS QTOF, for even more specific selectivity before ions reach the detection. The ion can go to a collision chamber and a second quadrupole as seen before for MSMS, and also to increase selectivity ahead of the detector. Alternatively, the ion can be directed to an ion trap for concentration, which will allow the system to reach much lower limits of quantitation and detection. A number of hybrid systems exist on the market for various applications, but GCMS and LC-MS-MS are the most broadly used, while LC-QTOF and LC-QTrap are growing as we seek to measure lower concentrations of contaminants at higher mass resolution, especially for the purpose of risk assessment.